Hello and welcome. In this video, we're going to be taking a look at AP Physics 1 Free Response Kinematics Review. Please remember to pause and rewind the video as necessary. Let's begin. In problem 1, it says to consider the following 8 velocity versus time graphs. There's our concept right there. Now it's also giving us a reference frame to adhere to, and that is that positive velocity is considered forward velocity. Let's remind ourselves what concepts link themselves to velocity versus time graphs. For instance, acceleration is the slope of a velocity versus time graph. And displacement is the area under a velocity versus time graph. Now, when I say area under really means the area bound between the graph and the t-axis. So let's take a look at letter A. We want to rank these objects A, B, C, D, E, F, G, H based on their acceleration from most forward, meaning most positive constant acceleration, to most backwards, most negative constant acceleration. If any two graphs show the same acceleration, put an equal sign next to those letters. So we need to rank all of our accelerations. Let's start by doing that on each graph, and that will help us rank them accordingly. So acceleration is the slope, so let's take the slope of each graph one at a time. First graph, we have a slope of negative 20 and a rise of negative 20 and a run of 4. This would be an acceleration of negative 5 meters per second squared. Graph B, we have a rise of 20 and a run of 4. That would be an acceleration of positive 5 meters per second squared. Graph C, similarly, we have a rise of 20, a run of 4. It's also an acceleration of positive 5 meters per second squared. Graph D has a slope of 0. So slope of 0, acceleration equals slope, means acceleration is 0. Means we're going with constant velocity, negative constant velocity specifically. Graph E. Graph E has a slope. Well, we could do it one of two ways. We could either go a rise of negative 20 and a run of 2, which is, of course, negative 10, or we could go negative 40 over 4. That's also negative 10. Again, slope of 0, acceleration 0. Slope here, we have a rise of negative 20, run of 4. And again, we have a rise of 20, a run of 2, or a rise of 40, and a run of 4. Either way, we get an acceleration of positive 10 meters per second squared. Now that we have all these accelerations calculated, we simply list them from most positive to most negative. Well, the most positive one here would be the last one we did, which is graph H, because that has positive 10. So we'll start that. The next most positive one would be the next down from 10 would be a graph, and I'm going to cross these off as we go, would be accelerations of 5. You can see that occurs with graph B and graph C. Both have an acceleration of 5. Cancel those. So I'm going to write B is equal to C. However, H was 10 and that was greater. So put a little greater than similar. Then the next lowest acceleration, less than 5, would be 0. That occurs twice, here and here. So we have D and F. So that's greater than D, which is equal to F. Both of those are 0. The next lowest speed would be -5. You can see that occurs twice, graph A and graph G. So that is greater than graph A, which is equal to graph G. Okay, and last one, of course, would be slope of -10, which would be graph E. Okay. Briefly explain how we determine the slopes. Acceleration is the slope of a velocity versus time graph. And using that information, of course, the accelerations were simply ranked from most positive to most negative. B, rank the objects according to their displacements. Now we need to rank the displacement, which would be the area. Okay, so let's go back, and I'm going to change the color on this one, so not to confuse the calculations. We're going to find the area bound within each graph. And similarly, the most positive displacement is the most forward displacement. And similarly, the most negative displacement is the most backward displacement. So we're still graphing from, or we're still plotting from most forward to most backward. So we're still doing the same. So starting with graph A, you can see that the graph itself, the area is just going to be that triangle right there. So that would be a height of, if we're talking about the area of a triangle, 1/2 base times height. So the base is 4, the height is 20. 4 times 20 is 80. Take half of that. We get a displacement of positive 40 meters. I'm just shading it a little bit of that right there. Why positive? Because the velocity is above the t-axis. Okay, I know the graph is going down, but that just means the velocity is decreasing to 0. You're slowing down. Okay, however, in fact, it's good to kind of note some of these things as we go down. We're slowing down going forward. Right? That's the negative, that's the positive, but overall we have negative constant acceleration. In this instance, we have positive velocity. Since we're still going forward, it's positive displacement. In graph number 2, we have the same area bound, but this is going to be negative 40 meters because, of course, it is below the t-axis. This graph here, you can see is a positive 40 meters. Graph D is going to be negative 80 meters, right? 20 times 4, but negative 20, since you're below the t-axis, it's negative displacement. Now with this one, we're going to find the area of this and the area of this, right? We're going to add those together. So the area of this one, of course, would be 2 times 20, which is 40. Take half of that would be positive 20 for this half, and negative 20 for this half, for a total displacement of 0. Right? 20 minus 20 is 0. Here we have all of this, positive displacement, positive 80. Here we have this. Negative displacement, negative 40. And here again, we have a similar situation. Negative 20 meters here, positive 20 meters here. Displacement again is 0. Okay, let's go ahead and rank those. Most positive, of course, would be graph F. That would be the most forward displacement. Now that's going to be greater than a lot of them. It's going to be greater than letter A, which is 40, but count how many have 40. A, C, and that looks like it. Okay, so A and C, greater than A is equal to C. And we'll go ahead and cancel these ones. There we go. Okay, now the next lowest one, lower than 40, would of course be 0. That happens twice, E and H. Okay, and the next one, we're going negative 40. So negative 40 happens twice, B and G. So H is greater than B, which is equal to G. And then, of course, the lowest one would be negative 80, this one right here, which is graph D. Okay. Now in number C, letter C, it says rank these objects by their distance traveled. Well, what's the difference between displacement and distance? Distance has no negative value. It's the absolute value of displacement. Okay. In other words, it's the total length traveled. So in many cases, I'm going to do this in a different color here. I'll do this in gray. So in this case, since it's forward positive displacement, the distance is also 40 meters. Here, the 40 meters traveled, the distance is also 40 meters. You're just moving from a backward displacement. You're just moving backwards, but the total length of it is still 40. The distance is here still 40 meters. The distance here is 80 meters. Yeah, it's backwards, but doesn't matter. The length is still 80 meters. Here we go 20 meters forward. We're slowing down. We stop, and then we go 20 meters backwards. But what's the total distance traveled? Total distance is 20 plus 20, or 40 meters. Total distance here is still 80 meters. Total distance here is 40, even if it's in the negative direction, it's still 40. Total distance here is still 40. So now we're going to take those and we're going to rank them. We have a lot of 40s. Now the largest one, of course, would be D and F. D and F are both 80. So D is equal to F. And 80 is greater than a bunch of 40s. Well, how many 40s do we have? A, B, C, E, G, H. A, B, C, E, G, H. There's a lot of them there. A, B, C, E, G, H. And they're all equal. So again, displacement is the area under a velocity versus time graph. Distance is the total length traveled. Distance has no negative value. If we were to ask to rank average velocity, well, which one would we use? Part A, B, or C? Well, average velocity is the rate of change of displacement so we would use part B. Part B was a ranking of displacement. Okay, now, so in order to fill out this next part in terms of part E, explain in words what the object is doing in the following graphs. Use words like moving forward, moving backwards, standing still, speeding up, slowing down, and constant speed. What we'll do is let's go back to each graph and let's quickly label what's going on with them. I did that for the first one. We're slowing down, but we're going forward. You're going from velocity of 20, negative 20, to 0. You're slowing down. This time we're slowing down again, moving backward. That's why the two negatives account for a positive constant acceleration. Okay, here we are speeding up. Because you're going from 0 to 20. You're speeding up going forward. These two positive attributes correspond to a positive constant acceleration. Here we have negative constant velocity, negative slope. Graph E. Well, graph E, what we're doing here is we are doing a couple things. And I'm going to highlight them in different parts. Over here on this side, we are slowing forward. Right at that moment there, we are stopping. And this part of the graph right here, we are speeding up, going backward. Those account for your negative acceleration. Slowing down, going forward, those account also for the same negative acceleration. Positive constant velocity in graph F. Here we are going from 0 to negative 20, so we are speeding up. But we're speeding up going backward. Those two qualities give us a negative constant acceleration. And here, again, we are, during this segment here, we are slowing. Okay, how do we know we're slowing? Because we're going from 20 to 0. Right here, we're stopping. So we're slowing, going backward. Slow, backward. The two of those give us positive acceleration. We stop right at that moment there. And here, for this chunk here, from 2 to 4 seconds, we are speeding up, going forward. And both of those are positive, also giving yield to the same positive acceleration. Okay, so let's see what's going on in each one. In graph A, the object is slowing down, going forward. Going forward. In graph B, we were slowing down, going backward. Graph C, we were speeding up going forward. And then in graph D, we were going with negative constant velocity. So graph C, we were speeding up. Going forward. And graph D is moving with constant speed. Then we're going to skip to graph F and then graph G. Graph F is also moving with constant speed. And graph G is speeding up going backward. And then graph G speeding up going backward. Now in part F, we want to be able to rank the positive, we want to rank the net work done. So positive net work is when an object is done on an object if the object gains kinetic energy. This is work kinetic energy theorem. The net work done on an object is equal to a change in kinetic energy. So if it gained kinetic energy, positive work was done. If you lose kinetic energy, negative work was done. So part F1. For which two objects was the net work positive during the 4-second interval? So in other words, we want to know which one gained kinetic energy. Well, that would be the ones where you're speeding up. That would be C and G. If you're speeding up, you're increasing your kinetic energy. Which ones had negative net work done during the 4-second interval? Well, that would be the ones where you're slowing down. A and B. Which objects was the net work 0 during the entire time? So the net work was 0 when you had no change in kinetic energy. So no change in kinetic energy would occur. Constant speed. But then it would also occur when the displacement ended up being 0. And this is why, and the reason why is because if we looked at the change in kinetic energy, the change in kinetic energy here would be relating to a speed, not a velocity, but a speed of 20, and then at the end, at 4 seconds, a speed of 20. The speed never changes really, therefore the kinetic energy never changes. So that is true for H and E. So D, E, F, and H do not show any change in kinetic energy. Explain your answer for graph G. Why does it have positive net work? So graph G has positive net work Because the object is speeding up. Meaning it's increasing its kinetic energy. The increase in kinetic energy results in positive net work being done. Explain your answer for part E. Why does part E have zero network? Because the object starts at 0 seconds with a speed and ends at 4 seconds with the same speed. Since there is no change in speed, there is no change in kinetic energy. Therefore, there's no network done. Part G. Which graphs could represent a cart with frictionless bearing on this incline? Explain your reasoning. All right, so what would be done? Well, you're moving forward, so you'd want all the graphs that essentially were above the axis. Okay, but you would be slowing down. And you think about it, you're going uphill, you'd have to be slowing down. So we're slowing down going forward. Okay, so let's take a look at which ones could be represented with slowing down going forward. Graph A, graph B could work too, because graph B could represent the cart coming back down the incline. So graph A would work. Graph B would work. You're slowing down, right? But then you're going backward. And let me see. No, not B. Graph A would work. Here we are. Graph E would work. You're slowing going forward, you stop, then you're speeding up going backward. That would definitely work. And then, there we are. Graph G would work too. Speeding up going backward. Graph A, cart moves forward while slowing down. Going up the incline, you'd be slowing down. Graph E, cart slows while going forward, stops, then speeds up going backward. And then lastly, graph G would work because the cart, if the cart could start from rest at the top and speed up going backward. Okay. All right, so now part H, we're going to take a look at these motion maps and we're going to match them to each one of the graphs. So first things first, let's figure out what each type of motion represents, then we can match it to those exact type of motions in each graph. So what I'm seeing here is the arrows are all pointing forward and the arrows getting longer and longer each time. That tells me that we're moving forward. Since the arrow's getting longer, that tells me we're speeding up. We're accelerating, right, going forward. We'll match that with a graph in a second. Over here, well, kind of looks like the arrows we're going to the left, so we're going backward. But it seems as though the arrows are getting smaller as we do, so that would be an indication of slowing down, going backward. Here, the arrows are moving forward. Seems as though the arrows are getting smaller, so we're slowing down, going forward. Here, we're going forward with positive constant velocity, so constant speed going forward. Here we have a change of direction. We seem to be starting here. We are slowing forward, stop right there. Then we are speeding backward. All right, in this graph, we appear to be slowing, going backward. Then we stop. Then you are speeding forward. Here, we're clearly going backward. The arrows are all pointing left. Okay, but the arrows are all relatively the same length and evenly spaced out. That would be an indicator of constant speed in this motion map, going backward. And here, again, we're going backward. All the arrows are pointing left. But the arrows are increasing in size, so it looks as though we are speeding up, going backward. Okay, so if we match them up, okay, speeding up going forward, speeding up going forward would be graph C. Slowing down backward. Slowing down backward would be graph B. Slowing down forward. Slowing down forward. Which one is that? Oh, right here. Graph A. Constant speed forward. That would be graph F. Slow forward, so slowing forward, stop speeding backward. That would be graph E. The other one, of course, would be graph H. So this would be E, this would be H. And then we have our constant speed backward. Our constant speed backward would be graph D. And our speeding up backward, that would be graph G. In problem number 2, we have an elevator that starts at rest on the ground floor. The elevator moves so that its acceleration is shown as a function of time below. We're looking at an acceleration versus time. And what do we know about an acceleration versus time graph? Okay, this particular motion graph has the following concept. The only thing we can do with it is find the area. And the area under equals velocity. Positive area, positive velocity. Negative area, negative velocity. So it's the area, of course, bound between the graph and the t-axis. Zero area would mean no velocity. Or zero area would be no acceleration, constant velocity. Okay, let's begin. Part A. Is the elevator moving upward, moving downward, or at rest at time equals 12 seconds? Right there. If the elevator is moving, state its speed. In any case, state your reasoning. Well, here's what I notice. The acceleration is 0. Remember, there's two cases where acceleration 0 means something. When we're at rest and when we're moving with constant velocity. Well, here, acceleration is 0 for 5 seconds. Remember, the elevator starts at rest. So this part right here, velocity equals 0. Now we have this chunk right here. If we find the area of it, we have a base of 5, a height of 2. We clearly have an area or a velocity of 10 meters per second. So the elevator will speed up from 0 to 10 meters per second during this time interval here. Since the elevator is in motion during this time, this is another time of 0 acceleration. But this time it's going to be constant velocity because you already have velocity. So what velocity will it be at 12 seconds? It'll still be 10 meters per second. This is a statement of Newton's first law of motion. Objects in motion, in the absence of a net force, if you're not accelerating, you don't have a net force, right? Will keep moving at that same velocity. So the elevator was moving at 10 meters per second, and there's no net force, therefore no acceleration during this next 5-second interval, then it'll keep moving with constant velocity of 10. The elevator is moving up at a constant speed of 10 meters per second. During 5 to 10 seconds, the elevator increased its speed by 10 meters per second. At 12 seconds, the elevator is no longer accelerating. And therefore keeps moving at 10 meters per second. Is the elevator moving upward, moving downward, or at rest at time equals 22 seconds? If the elevator is moving, state its speed. In any case, explain your reasoning. Well, 22 seconds is way over here. And clearly you can see what's happened is we have a reduction in speed. Here, during this 15 to 20 second time interval, the speed is dropping. Here the speed increased from 0 to 10. So the speed increases by 10 meters per second over these 5 seconds. The speed stays at 10 meters per second until 15, and then the speed is reduced by 10 meters per second. Well, if you're at 10 meters per second and you reduce it by 10 meters per second, that means you're back to 0 speed. It means you're at rest. Elevator stopped. From 15 to 20 seconds, the elevator is slowing down from 10 meters per second to 0. It's slowing down by 10 meters per second. The elevator would therefore be at rest at 22 seconds. Part C. At time t equals 25 seconds, is the elevator above or below its initial position? Or has it returned to its initial position? Justify your answer. At 25 seconds, the elevator is above its initial position. It increased its velocity going upward by 10 meters per second. It then slowed down to a stop. Problem 3. A world-class runner can complete a 100-meter dash in about 10 seconds. Past studies have shown that runners in such a race accelerate uniformly for a time t sub u, and then run at a constant speed for the remainder of the race. A world-class runner is visiting your physics class. You are to develop a procedure that will allow you to determine the uniform acceleration a sub u and an approximate time value of t sub u for the runner in a 100-meter dash. By necessity, your experiment will be done on a straight track and will include your whole class of 11 students. A. By checking the list of the line next to the appropriate item in the list below, select the equipment other than the runner and the track that your class would need to complete the experiment. Well, this, ladies and gentlemen, is an example of an LBQ. That's known as a lab-based question. Now, there are two types of lab-based questions. One type of lab-based question is a data processing question in which you're given data in a data table. You're usually asked to graph that data table and find something with the slope, y-intercept, or area in the graph that is physically meaningful. Sometimes you have to straighten the data, meaning you have to linearize it by taking one column of your data and squaring it or square rooting it or doing something to your data. So some type of lab-based questions are data processing questions. The other type of lab-based question is what's called an experimental design question. Experimental design questions are actually the easiest questions of all. You still have to know your concepts, okay? And this concept is, of course, constant acceleration and constant velocity. Constant acceleration and then constant velocity. Because we are told that we accelerate until this time here, and then we run at a constant speed for the remainder of the race. So the best way to attack a design question, experimental design, LBQ, is to actually not do part A first. And the reason it would not be a good idea to do part A first is because if you check off a certain piece of equipment and you do not mention it later on, you will not get the easy points for part A. It's almost best to take the problem and actually work it backwards. So that's essentially what I'm going to do. I'm going to work the problem backwards. Okay, now again, you have to know what the concept is. Well, the concept is, of course, constant acceleration with constant velocity. Now, what we're going to do is we're going to space out the students. So in part B, it's asking to outline a procedure that would help us determine A sub u and T sub u, including a labeled diagram of your experimental setup. That's probably a good place to start, is always with a picture. You first identify the concept, okay, or concepts that are going on in the problem, and then build an image of what is going on. Then relate that image to certain variables. Okay, the variables would be the data you're taking. One variable that is going to affect the other variable is the dependent variable, or the y variable. The other variable ends up being the independent variable. Now, in this situation, we're doing a kinematics-based lab, constant acceleration and constant velocity. So we're essentially going to be making a position versus time graph. So we know we have to measure position and we know we have to measure time. That's pretty easy. Okay, let's go down to the bottom of part B and let's draw an image of what this might look like. Okay, I'll have a runner. Okay, and then what you're going to find, this is the starting line right here, 0. At every 10 meters, what we can do is we can place one person from the class. Oops, put 50 twice. Put one person from the class, like this, until we get all the way to 100 meters. And each person in the class is essentially going to be holding a stopwatch. So we're going to put another person here at 20. We'll put another student here at 30. We'll put another student here at 40. Another one at 50. Another one at 60. 70. 80. 90. And 100. And what this allows us to do, essentially, is build the length of time it takes the runner to reach that particular position. Because as you can see, each student is placed at a 10-meter increment of position. So we can use, well, let's see, what could we use? What could we use to measure this? Well, it seems to me we could either use a ruler or a tape measure. Tape measure seems probably easier. Right? We need a tape measure to measure out the distances, and clearly you need a stopwatch in order to measure the time. I'm only going to write the stopwatch one time because all the other students have one too. And so when you do something like this, it allows you to think the problem, well, backwards, really. You're thinking about the overall big picture. Think of the big picture first. The big picture is we have students at positions. They're going to use their stopwatch to measure time. And once we have that into play, then we can map out the details. The details would be the procedure. Okay, so what would be the procedure? Now we can kind of spell it out. We would spread out the students every 10 meters using a tape measure. Now, every time I mention a piece of equipment that I'm going to use, I check it off up here. That way my checklist matches what goes on in my description, in my procedure. Remember, a procedure is nothing more than just a list of steps you're going to do. And physics procedures are always pretty short. Next, as the runner starts, each student starts their stopwatches. So in other words, all students are synchronized to the same 0 time. They all start their stopwatch at the same time. So I'm going to mark off stopwatch. As the runner passes each student, They stop their stopwatches and record the time it took to get to their position. And so there we go. We have a pretty easy procedure with only a couple pieces of equipment, but each equipment needs to match a particular variable you're trying to measure. Time and position, right? Those are the only variables involved in this particular lab. And that's what you have to think about when you do a lab-based question design, experimental design, is what concept is the overall big picture? What variables are relating in this concept, and therefore what would have to be measured? And if I know what has to be measured, I can then work it backwards to think, oh, what equipment I might use to measure that variable with. In this case, I'm measuring position and time. Therefore, I would choose a stopwatch and a tape measure to do so. Part C. Outline the process of data analysis, including how you will identify the portion of the race that has uniform acceleration and how you will calculate the uniform acceleration. Well, ladies and gentlemen, this is really done using graphs and equations. So, first thing, we'll make a graph of position versus time. And it would look something like this. At TU, right about, the graph will be accelerating from rest. And so you would expect the graph to be concave up during that point right there. I'm going to make that a little shallower right there. There we go. Like that. Starting from 0, you would expect it to be concave up, curving, right? Showing you positive constant acceleration during that point right there. Then for the remainder part of the trip, it's going to keep the same slope upward like that, all the way to 100 meters. That would be positive constant velocity right there. Now, a couple of things that we could do. TU can be found by looking where the graph transitions from a curve to a straight line. And then lastly, we can use x equals x naught plus v naught t plus 1/2 at squared, which by the way reduces significantly to x equals 1/2 at squared, to find a sub u. Now we could also use v equals v naught plus at, cancel v naught. We could use this, what we would have to do is we would have to find what this constant velocity is, and we can do that by finding the slope, okay, and then we could kind of work it backwards. We know how much time the acceleration is occurring, so we could feasibly figure out what that would be. The final velocity here would be the same as the constant velocity for the rest of the way. So you could use that equation to figure it out as well. the acceleration. All right, and that concludes problems 1, 2, and 3 from AP Physics Review, Kinematics Free Response.